Hey,
Hello,
Ali.
everybody. Good morning in the USA and good
Yeah, good
afternoon for
morning,
the rest of
USA.
the people.
How are you doing,
Yeah,
Ali?
yeah, I'm good. Very busy with our next event in Europe, in Nuremberg, Germany. Last week we were talking with Jonas about APEC, and he was telling us um, a little bit how was his impressions about it. I think it's good to chat with you about a little bit about APEC and what was your impressions. Um, I imagine you could meet a lot of clients and new prospects, so I think this is good.
Yeah, let me share here in the chat with everyone a post I wrote, let's say, or an article. Oh, sorry, it's not available. So I would put it later. We can share later. But I wrote an article about APEC and the artificial intelligence discussion at APEC because after a lot of years of thinking in the artificial intelligence for power electronics, this has been the first time that really we saw presentations and people talking about that um, in a different way than before. So summarizing, let's say in the last 20 years or even 40 years, from time to time you see an article that use data for training a model, a neural network, to do something in power electronics. And this is not new. But this year, somebody used LLMs to do something in power electronics. It could be like just bill of material analysis or just running a simulation, the design simulation or whatever. So I think that it's really something happening, and that for me was like the main, the new thing to remark from this APEC. The other thing from this APEC to say is that usually APEC, when it's not happening in the West Coast, the number of attendees drops significantly. And this year, I think we were 4,700. Um, what is a little bit better than I think that the people expected from a location like Atlanta that is not, let's say, very fancy for a lot of people to go there. But I have to say in favor of Atlanta that it was a great city. The weather was perfect. The people of the city were very nice. So in the restaurants, in the shops, and everywhere, I felt like the people were very nice with us, and I was like, yeah, enjoying the time there, and also the organization I think was very good. And something also new this year is that they removed the sessions on Thursday afternoon, which is something that everybody was hating. So nobody wants to make a lecture on Thursday afternoon because nobody is there. Actually, I'm usually just traveling on Wednesday. So I'm not even at the show on Thursdays. And yeah, I mean, they removed that. Still, there are presentations on Thursday morning, what is I think is fine, but they removed the Thursday afternoon, so everybody can go home on Thursday afternoon of the event. Okay, so let's move to the topic of today. I can start sharing my screen. Um, by the way, I think that you are choosing very good songs every weekend. You're improving on that. And I feel like this is, I mean, at APEC, the people is also pitching music, and this is this type of music. So I think that we are entering the same mood.
So, no Miley Cyrus. I love Miley Cyrus music, but honestly, maybe it's not appropriate for electrical engineers.
Okay, so let's go directly to the agenda of today because I think that we will have a few. webinars about this topic if the people find this interesting. So what I'm going to do today is going to review a converter design process described by Texas Instruments that actually they did it at APEC, and I think it was extremely good. And then we will move to the magnetic design process that actually was not described in that webinar. And we will try to do one example in the step one, and you will discover what this is step one, in my opinion, and we'll have some time for Q&A. So, so the presentation that Texas Instrument team, two great presenters, we're doing is called Fundamentals in Power Electronics. And they did two examples. One is for a back design, and the other one for a flyback converter design. The first one was done by Pradeep. I mean, I in contact with him. He's an amazing power electronic engineer and manager. And the other one was by Brian King, that he did an excellent presentation. And they explain like a procedure for designing a flyback. And they talk about the specifications, choosing a controller, then thinking that the flyback is connected to the grid. So choosing the AC rectifier plus the capacitor, some basic calculation for the transformer that I'm going to affect the rest of the design. And then choosing the semiconductors, closing the feedback loop, and then there is a point here, the transformer design and construction. We will go more in detail. So for this application, they choose for this example, they choose a plug-in air quality monitor of 10 watts, and then they create these specs. So when you analyze all these steps here, it could be like if you take a look to this presentation that probably will be online at some point, free for everyone, you will see that there are a lot of equations and design decisions and all this stuff. So what I did is I created Python code. I created a Python code for doing all these steps at once. So just putting the input voltage, output voltage, and the power, this system can just create your case. So if I update these to 40 watts flyback, and I run this here, we can see, let's say, the information to choose the right capacitor at the input, and the controller design that actually was the most interesting for me, because I have, let's say, this is a IC controller for Texas Instrument for flybacks, and let's say the part that is more kind of critical for me is to choose all the parameters for that controller design. So assuming, let's say, that we want to have, let's say, some specifications of ripple in the output, current ripple, these choose all the parameters of the inductors, of the resistors and capacitors for that case. And then I connected all this information with a KitKat project here that is a schematic that now I'm working also in the PCB. I will let this open at some point for everybody, and it will be integrated in Frenetic AI, where all these parameters are, let's say, all the resistors are calculated in the other code. So if you want to design this flyback using the UCC 28748-42, this is going to do most of the job automatically. But when I spent like a few hours doing this process proposed by TI, I realized that there is one point that is not explained at all. So they work in the selection of the device, everything, okay, calculation of the tune rate of the transformer. But at some point, we arrive to the transformer, and it's like, I remember in the presentation that Brian said, like, okay, go to the exhibition bar and then look for somebody that is going to help you to make the design, because it's not so simple. So you can see here, they just describe that, okay, the specification for a supplier. So what I'm going to do today is to explain to you a little bit what you can do here and why the first step is so important. So take a look at this information here. So once the design of the parameters like tune ratio, inductance, and even selecting a switching frequency are done, then you have to calculate, here there are some calculations of, okay, this is the peak current, this is the RMS current in the primary, in the secondary, and the auxiliary. And they show you this construction for this transformer. If you look in the paper that they are talking about here, what you will see is a description. Let me show that to you. You will see a description like this. Yeah, this paper that is like has more than 30 years ago, and it's very, very nice. It's explained to you how to choose the core. But if you go to more detail, you realize that the losses, especially the proximity losses, are just a kind of approximation using Dowell parameters. So what I'm going to do right now is like, okay, we have a clear process according with this TI document. We have a clear process for the Hall converter, that for the transformer of the magnetic, depending on how you want to call it. We don't have a first, let's say, a procedure. So what I want to show you today is that for that component, the way that I see that procedure is in these three steps. So the first step is that we need to design, or let's say to define the waveforms and the operating conditions that we will use for the design. Because at the end, when you're doing a design of magnetic, you are going to choose a core, you are going to choose a winding and make the design. I mean, the description, or how do you want both things to be positioned, and then simulate and iterate about how the losses of these selections you have done are working. In the middle, we have the design algorithm. So if we already have the initial specs and we want to have a prediction, first we have to make the design. And in our case, we have our own algorithm that every manufacturer or every person can have their own algorithm. But today we are going to focus on step one. So I'm going to explain and review why step one is so important and how this can affect the your results at the end if you don't do this properly. So let's move that bar. So well, first I'm going to create the design for data specs. Let's say 200 volts input, or that was like a 50 volts input, 20 volts output, and 40 watts. And while this is doing the calculation for the design, I'm going to move directly to the flyback case of the, let's say, of the magnetic, because here we are just generating the design. But assuming that we already have that values, and I'm using Frenetic because it's our tool, but you can do this, let's say, by your own, or manually, or however you want to do it. So, so as you can see here in this flyback, what we have here is some specifications regarding the parameters like the inductance, the frequency, voltage, and power. And these specifications that correspond with the specifications that we saw previously in the TI document are the ones that we are going to use to generate a waveform. So let's say that I'm going to start from scratch just for you to show how this process will look like. So let's take a flyback, and then everything is going to be empty. So this is empty. So I start including the information, 50 microarrays, 100 kilohertz. 40 watt. 20 volts. Let me see what is the proposal of the tune ratio. Tune ratio is 7.25. That's open them. 7. So as you can see, there is no waveforms. So there is no values to make any kind of design. So now what we are doing is, okay, now we generate the waveforms. And the most important part here, we generate the values of RMS, peak voltage, peak current, and well, the DC current is not going to be very relevant at this moment, but also we have that value. And we can see that for each winding. In this case, we have only primary and secondary, but you can have more windings. Let's say that you have auxiliary, another secondary that is here for 12 volts and for just 1 watt. So if you have that, then you have another secondary. And again, you have to check here the RMS current and all the information for doing that design. And why this is so relevant? Why? The main reason this is so relevant is that these parameters are going to be changing when you're doing the design in all the conditions. Let's say that you're doing the design for that controller that Texas proposed. So if you check the controller, you realize that the controller maximum that the cycle is 0.5, that there is a variable frequency depending of the load. So there are some frequency variations. So if I change, look at this number, for example, here, 0.49 and the, let's say, and the RMS voltage 137. If I change this value here, so this is changing, and this is changing just because I changed the frequency, but it's gonna change for every point. So if I add another operating condition and say like, okay, this is gonna be 50. What I can see in a kind of report is that let's say the values for the peak are going to be very different. So in both cases, for example, peak current and peak current in the secondary, actually in the secondary, the peak current difference is 50%. So it's very, very relevant. And the problem is that once, I mean, if you are not taking all this information for your design, it's impossible to really get calculations that you will need for the future. I mean, for the predictions of the losses and everything. So, for example, if let me create a design here. So if I create a design, and what I'm going to see is that this is my step 2, and this is step 2 is using our algorithm, but you can use your own algorithm. But I'm going to use these for showing you the impact in the losses for those cases. Let the design finish. Here we can see, okay, we have a design. Okay. Let's load the design. So now we have used the conditions for the design on the operating point 2, that means 50 kilohertz. And now if we analyze the losses for these 50 kilohertz and let's say 100 kilohertz, sorry, that was actually in point 1. And the 100 kilohertz here, and we analyze the losses for both cases, we will see that we have different losses in for one frequency and for the other, and everything is related with the step 1 of the definition of the waveforms and the calculation of the peak and the current values. So that's the reason why this step is very relevant. And maybe you are thinking like, well, but having the RMS value and the peak value for a flyback triangular waveform is not very complex. And maybe I can have a spreadsheet for doing this. And it's like, it could be. So you can do that, and that will help you a lot for doing the design. But let me show you another case where maybe that is going to be very different. So imagine that instead of a flyback, you're going to have, let's say, for example, a CLLC design. So if you're having a CLLC design where you have 2 resonant frequencies in the primary and the secondary, you have let's say a frequency, a switching frequency that move depending of the power. These values here are extremely complex to calculate. So this is very difficult. So every time that you are doing here a chain, let's say that I'm changing, this is a case with 500 watts, 400 volts input, and 48 volts in the output. And I do a chain here. Let's say I'm testing for 400 watts. The calculations here, the values here are extremely complex to calculate because they are now a new switching frequency. So then this new switching frequency is changing these values, and you have to consider all the resonances here and all the things. So that's the reason that in the step 1 is very important. And the other thing that I wanted to show you here why this is also affecting everything is that if you are able to consider all the harmonics, this is the FFT of the waveform, you will see something very important. That is like, this is how the waveform looks like. This is how the harmonics for this waveform looks like. So when you are going to do the losses in the winding, here, if you just use the simple double equation, the only thing you can do is to calculate a relation between the DC resistance and the AC resistance. And that is a good approximation for when you have just 2 layers. But once you are starting to have a kind of, for example, in this case, an interleave case for reducing the leakage inductance, what you will see is that the relation between AC and DC is just not as simple as just a coefficient. You need to really take in consideration what is happening here for each, let's say, what is the current through each of these terms, what is the current in the other secondary, and then calculate how we're going to have the proximity losses and the let's say the effect between one and another. And the crazy thing is that for flyback, both windings, I mean, primary and secondary are not conducting at the same time. So you have primary conducting and secondary is dead. I mean, not dead, but it's 0 current. And in the other way around, that you have the third auxiliary that is conducting all the time because it's like supplying maybe the, I don't know, it's supplying the chip, for example. So it's extremely complex to calculate how it's going to be the losses here due to the current. But if you don't have the currents and the harmonics of those currents, it's going to be even much more difficult to calculate accurately the losses, and especially when we are talking about high currents. So I think we are going to run out of time, so I want to let some minutes for questions before closing today's webinar. So let's see if I think we have at least let's say one question. Oh, well, was one comment. So is there any question today for the impact of generating the waveforms and calculating the RMS and peak values? And if you're, let's say, want to describe RMS and voltage for each harmonic, that would be ideal.
In the meantime, I would like to comment to everybody in this webinar that all of you who have registered with your work email are going to receive access to Frenetic AI. It's the first screen Chema has shown today. So if you want to access Frenetic AI and have joined this webinar with Gmail or other free emails, you can go to the link I have shared in the question and answers, and you can join the wait list. So you will have tomorrow the access. We have a question. Comment.
Yeah, I mean, well, thank you, Lázaro. Lázaro, everybody in California, we have been suffering for the other schedule. So our idea is that we will have a specific schedule for California that is actually this schedule. If the people is asking us for starting a TV late in the US, also we can try. I'm based in San Francisco, so this is also a good time for me. Okay, so looks like not very technical questions today, but I hope that that means that I hope that everybody understood the point, and see you next week.
Yeah, thank you everybody to join today. Bye bye.
Thank you. Bye bye.